Hello and welcome to Chemistry with Dr. Clark. In this video I'd like to talk about predicting ionic charges based on the number of valence electrons in an atom. Now the easiest way to do this is using some Bohr diagrams. So if you're having some trouble with Bohr diagrams, it might be a good idea to stop here, go back to one of my previous videos that talks about how to create a Bohr diagram, and then come back. But in any case, let's take a minute and do a quick review. In the world of Bohr, Bohr said that electrons live in very fixed distances from the nucleus. And that's what I've got drawn here. So here in the middle is my nucleus, and then there are some fixed distances, some rings, where the electrons are going to live. In the first ring, you're allowed to put 2 electrons. In the second ring, you're allowed to put 8. And in the third ring, you can put in 8 as well. So if we were to just draw a few of these, for example, take lithium. Lithium has 3 protons. So if I look at my nucleus, I've got 3 protons living in my nucleus, and I've got 3 electrons living in the rings around the nucleus. So the first 2 electrons can live in the first ring, because that first ring can hold 2. That means the third electron has to be out here in the second ring because there's not enough room in the inner ring. So if we look at this picture here, we can start to talk about valence electrons. Valence electrons are the electrons that are in the outermost orbital, the outermost ring, the outermost shell, right? There's a couple of different ways to talk about it. But if you're talking about rings using Bohr, this would be the outermost ring or orbital. So for lithium, there's 1 electron in this outermost ring, so it would have 1 valence electron. If we talk about aluminum, aluminum has 13 protons. So let's put 13 protons here in the middle, in the nucleus. So that means I have 13 electrons that need to find a place to live. So you always start filling from the middle and you work your way out. So this first ring can hold 2 electrons. So let's put 2 there. 1, 2. Now you had 13. You've just used up 2 of them, so you're down to 11. The next electron has to move to the next ring. So the first ring can hold 2. It's completely filled. So now we're going to move to the next ring, the next orbital. This orbital can hold 8, and I have way more than 8. So let's put in 8. 1, 2, 3, 4, 5, 6, 7, 8. So I now have 8 electrons in the second orbital. It can hold 8, and I've put in a full 8. So if you had 11 electrons, you just used up 8 more, you're down now to 3. That last 3 electrons has to go into the next orbital. So let's put those 3 here. 1, 2, 3. Now, in the world of atoms, there are 2 types of electrons. There are the electrons that are in the inner orbitals. We call those core electrons. And there are the electrons that are in the outermost orbital. Those are our valence electrons. So for this atom here, the outermost orbital has 1, 2, 3. So I would have 3 valence electrons. All right, let's move on to oxygen. Oxygen has 8 protons, so let's put my 8 protons in the middle. The first 2 electrons will go into the first ring. There you go. So I had 8. I've just placed 2 of them, so I'm down to 6. This next ring, or orbital, can hold 8. But I don't have 8, right? I've only got 6 left. So all 6 of these will go into this second orbital. 1, 2, 3, 4, 5, 6. So that gives me 6 electrons in this outer ring. If this is the outermost ring, that's my valence electrons. So for the oxygen, I would have 6 valence electrons. All right, one more. Let's talk chlorine. Chlorine has 17 protons, so 17 protons. The first 2 go into the first ring. So I had 17. I've just used up 2, so I got 15 left. The second ring, or orbital, can hold 8, and I've got way more than 8. So let's put 8 in this second orbital. 1, 2, 3, 4, 5, 6, 7, 8. So I had 15 left. I've just used up 8 more, so I'm down to 7. This next orbital can hold 8, but I've only got 7 left. So I can fit all 7 of those in this outermost ring. 1, 2, 3, 4, 5, 6, 7. So if we were to count all of the electrons, I would have a total of 17 electrons because you have 17 protons. And in an atom, you have to be electrically neutral, right? The total number of protons has to equal the total number of electrons. If you're talking about valence electrons, those are the ones in the outermost ring. So in the outermost ring, I have 1, 2, 3, 4, 5, 6, 7. So I would have 7 valence electrons. Now, the reason why valence electrons are so important, imagine 2 atoms. You have an atom here and you have an atom here. And they're going to come together and do some sort of reaction. Well, as they come together, the part of the atom that touches first would be these outermost electrons, right? Outermost electrons here, outermost electrons here would interact. So in the world of chemistry, if you're going to talk about ions or ionic compounds or molecules or covalent bonds, the interaction is always about the outermost electrons. So your valence electrons are the ones that will interact with the neighbors. These inner ones, right? If you take a look at my chlorine, this inner ring here, that's on the inside of my atom. It's too far away from the edge. These electrons are not going to interact with the neighbor, right? Same thing with this ring here. If you look at this second ring, again, it's totally filled, but it's on the inside. It's too far away from the edge of the atom to interact with the neighbors. So these are core electrons. If you're a core electron, you tend not to do anything, right? You don't interact with neighbors, you don't form bonds, they just don't get involved. Your valence electrons, that's where all the action is. Okay, so now that we've kind of reviewed how do you figure out the number of valence electrons, let's talk about how that relates to ions. Okay, so let's flip over. So let's say we go back to our sodium atom. Okay, you're given a sodium atom. I've told you there are 11 protons. So let's put the 11 protons in the middle. Now, this is electrically neutral, which means that if you've got 11 positives, you got to have 11 negatives, right? They have to balance. So I'm going to have 11 electrons. And just like a minute ago, I'm just going to put them in the rings starting at the middle and working my way out. So first ring can hold 2. Let's put in 2. So I had 11, just used up 2. So now I'm down to 9. The second ring can hold 8. I've got more than 8. So this second ring is going to be completely filled with electrons. 1, 2, 3, 4, 5, 6, 7, 8. So I had 9, just put in 8 more, so I'm down to 1. That one leftover electron has to go into the third orbital, the third ring. So let's put that one right here. Now, it turns out that in the world of atoms, if you have an orbital or a ring that's completely filled, that's energetically stable. Okay, that's stable, you like it, you love it, your life is great. If you have a ring, though, that's not completely filled, like this outermost one, that's unstable. That's energetically not a good thing. So this little sodium atom would really like to have all of its orbitals filled. Now, it's got 2 choices here. You could attempt to fill this orbital. But if you're going to fill the orbital, you've got to find 7 more electrons, right? This orbital can take 8. You've got 1, so you'd need to magically find 7 more electrons. 1, 2, 3, 4, 5, 6, 7. That's really hard, okay? Picture it as walking down the road and you find a quarter on the side of the road. You'd be very lucky to find a quarter. Well, now imagine trying to find 7 quarters on the side of the road, right? It is very hard to find 7 more electrons. What's much easier is if you take this electron and you just give it away. You say, hey, I've only got 1 electron in this outermost orbital. If I could get rid of it, then this outermost orbital is not needed. I don't need it anymore. It just disappears. And so what my picture does is it changes, right? I still have my 11 protons in my nucleus. You still have 2 electrons in that first orbital. You still have 8 electrons in the second orbital. But because you threw this electron away, you don't have need to even draw the third orbital. So now if I look at this picture, first orbital, filled. That's excellent. Energetically stable. If I look at the second ring, also completely filled. Also excellent. Also energetically stable. So this is much more stable than this. So your sodium would prefer to look like this than this. That's why sodium likes to give away 1 electron. Now, if we talk about electrically neutral, right, over here, you had 11 positive protons, you had 11 negative electrons, and basically they canceled out, right? Positives and negatives cancel. But on this side, you don't have a balance anymore. You've still got your 11 positive protons, but now you've only got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 negative electrons. Think of it in terms of math. If I told you that you had a plus 11 and a minus 10 and I asked you to add them up, positive 10 plus a negative 10, positive 11 plus a negative 10 would give me a positive 1. This would have a charge of positive 1. It's no longer neutral. And the minute something gains a charge, that's when it becomes an ion. So this would be a sodium atom because the electrons and protons match. This would be a sodium ion. And because it has lost 1 electron, it does gain a plus 1 charge. So that's how I put in my little plus 1. So if you know the number of valence electrons, you are now able to predict, are you going to add electrons or are you going to lose electrons in order to have only filled orbitals, filled rings? For the sodium, it has that 1 valence electron and it is going to lose it. So it does become a sodium ion with a 1 plus charge. Now, if we do talk about naming these things, if you have a sodium atom, it's a sodium atom. If you have your sodium ion, it's still a sodium ion. When you talk about things that become positively charged, right, anything that ends up with a positive charge, its name doesn't change, right? It was originally sodium, and it's still sodium. And what we're going to see in a minute is that when you gain a negative charge, your name does change slightly. Okay, so the positive ones, the name change doesn't happen, right? You go from sodium atom to sodium ion, sodium and sodium. All right, so let's say we do try a second one. Okay, let's cover up the bottom one here. Maybe we get, there we go, a clean sheet of paper. Let's say we talk about phosphorus. Phosphorus has 15 protons, which means it has 15 electrons. So you got 15 protons, you got 15 electrons, you are electrically neutral. If we put those protons in the orbitals, the first 2 electrons go into the first orbital, the next 8 electrons go into the second orbital, 4, 5, 6, 7, 8. So I've just placed 1, 2, plus 8. I've done 10. So you started off with 15 electrons. I've just showed you 10 of them right here. So that means you got 5 left. So there are 5 electrons to go into the third ring, the third orbital. So 1, 2, 3, 4, 5. Just like the sodium, this outermost ring is not filled, right? It's only partially filled. You have 5 valence electrons. Now, you've got 2 choices. You can either try and find some electrons and add them, or you can throw away electrons. Now, this is a very different situation than sodium. Sodium only had 1 electron, and it's easy to lose 1. You now have 5 electrons. You've reached the point where it's too hard to lose 5 electrons. It's much easier to find 3. Okay, this outer orbital contains 8. So if you've got like 1, 2, or 3, 1, 2, or 3 are easy to lose. We like to lose 1, we like to lose 2, we like to lose 3. But if you've got 5, 6, or 7, you're more likely to gain electrons because 5 is pretty close to 8. 6 is even closer, 7 is even closer. So when you're looking at whether you lose or you gain, if you've only got 1, 2, or 3, you'll lose. If you've got 5, 6, or 7, you're going to gain. So magically, you gain 1, 2, 3 electrons. Okay, so they're going to come in and I'm going to magically gain them. Now, I've drawn them here in red because really in this picture, they shouldn't be in this picture. Because in this picture, I should only have 15 electrons. So I do have 15 black electrons, but I've just slipped in 3 red ones. So really here, I should have just drawn my arrows to show that they were appearing, but not really put them in. That's why I have a second picture. The second picture will show them as actually part of the atom. So 15 protons. The first orbital still has 2. The second orbital, the second ring, has 8. And now, because I'm going to give 3 more, 3 plus the original 5 valence electrons will give me 8. 4, 5, 6, 7, 8. Now that you have all of the orbitals completely filled, you reach a low energy stable configuration, and then this thing is stable. So your phosphorus atoms, because this outermost ring is not completely filled, it wants to do something to fill it. It's reactive. It'll want to make bonds. It'll want to do chemical reactions. Your phosphide here, because all of the rings are filled, is a lot more stable. So let's talk about charges. Here you have 15 protons, but now you have 2 plus 8 is 10, plus 8 more is 18 electrons. You've gained 3. So if we talk about it in terms of math, this is like saying you got a positive 15 and you're going to add on a negative 18. So positive 15 plus a negative 18 gives me minus 3. So when I write this, this was a phosphorus atom. This is going to be a phosphorus ion, and it's going to have a charge of 3 minus. Right? This one had no charge because the protons and electrons matched. This one does have a charge because the number of protons and electrons don't match. By drawing the diagram, by knowing how many valence electrons I had, by knowing how many more I needed to get an octet, to get 8, I can predict the charge. And if we do talk about the names, this one was a phosphorus atom. Maybe we'll write it over here. So phosphorus atom. The negatively charged ions get a name change. Whatever their original ending one, this one ended in or us, the new ending is going to be an "ide." So this becomes a phosphide ion. There's a name change when your charge is negative. All right, let's move that up a bit and try one more. So let's say we're talking about a fluorine atom. Fluorine atoms have 9 protons. If you've got 9 protons, then you're going to have 9 electrons because the atoms are electrically neutral. So I'll put the first 2 electrons in the first ring. Now, you had 9. I've just used up 2, so that means you got 7 electrons left. This second ring can hold 8, but you've only got 7. So 1, 2, 3, 4, 5, 6, 7. This is a not completely filled orbital, right? It has 7 valence electrons, and it would really like to have 8. Okay, so it's not happy. So what I'm going to do, well, again, I had technically two choices. I could try and lose those 7 electrons. Yeah, you're never going to lose 7 electrons. That's way too many. What's more likely is that you're going to gain 1. Now, I learned from my mistake up here. I am showing the electron being added, but I haven't actually drawn the electron. Because in this picture, this is the picture of the atom. So in this picture, I only want to show 9 electrons, right? I don't want to squeeze an extra one in. That's why I have a separate diagram for the fluoride ion, because this will show the extra one slipped in. So if we redraw, 9 protons, the 2 in the first ring are still there. The original 7 valence electrons are there. And this outer ring would like to have 8, and we've decided that we're going to give it 1 more. So now the outer ring has 8 valence electrons. The protons and electrons don't balance anymore, so let's recount. I had 9 protons. I now have 2 plus 8 is 10 electrons. So that's 9 positives and 10 negatives. Positive 9 and a negative 10 gives me negative 1. So the symbol here would be fluorine atom. The symbol here is going to be a fluorine ion, but it has a charge of -1. That allows you to predict how many, what your charge is going to be. If we write the name, this was a fluorine atom. Because it is negatively charged, we're going to lose the original ending of "ine" and turn it into an "ide." So this becomes fluoride ion. So if you are able to draw the Bohr diagram and you're able to look at the number of valence electrons that you have, you should be able to predict whether you're going to lose electrons. We come back here to our sodium, right? Sodium lost an electron. Or you should be able to predict that you're going to gain some electrons. And based on the number of electrons you lose or the number of electrons you gain, you should be able to predict what the charge is going to be, right? You gain an extra 3 electrons, you're a -3 charge. You gain an extra 1 electron, you're a -1 charge. If you lost 1 electron, you're going to be a +1 charge. So knowing the number of valence electrons, you can decide how many you're going to add and lose, and therefore you can decide what the charge is going to be. Once again, I thank you for joining me here at Chemistry with Dr. Clark.